Thank you. So, good afternoon, everybody. Karel van Akker here. I'm very glad that I have the opportunity to talk to you this afternoon. To kick off actually the MOOC, I have a slight disclaimer on my presentation. So what I will give here is a personal view on e-waste recycling, and I will not cover everything, of course, that is dealt with in the MOOC. So I warmly invite you to also look at the MOOC for more details. For example, legal and social aspects will not be dealt in this presentation. So let's go on. It's blocked at my side. Yeah, I would like to deal with three questions with you. So what are the resource and climate impacts actually of materials consumption for electronics and electrical equipment? What are the more sustainable options to recycle, to keep our resources? And what are the challenges in waste of electronics recycling then? So let's go first for the resource and climate impacts of electronics. So if you look at mass meetings, for example, these are two pictures of elections of the Pope in Rome. You see clearly a difference in 8 years' time. On the left side, everybody is just looking at what happened at the end of the square. And the right side, everybody is filming things with the smartphone, with the iPads, and so on. So I have some questions with that. Of course, it's a nice evolution. Everybody is very well connected. We keep memories by filming and so on. But I'm an engineer, and I also have some questions with that. Questions such as, are there enough resources available? And what are the impacts of mining all these resources we need for making these smartphones, these iPads? And what is the impact on climate of production? And what about e-waste? Well, let's first look at the demand and lifetime of these equipments. If we just focus on smartphones, well, in the last 12 years, from the start that smartphones were sold on the market in 2007 till 2018, there have been more than 10 billion smartphones sold. And these smartphones, these devices have not a very long lifetime. And so the typical lifetimes are given in this table is about 1.5 or 2 years, which is a very short period of use of these complex devices. And on the other side, we have also predictions of the growth of the materials consumption, not only for these type of devices, but in general. That is really amazing and very challenging. These graphs show actually for different types of countries what a predicted growth in materials consumption, in resource consumption will be in the future. And we see that, we go from a 92 gigaton in 2017, we will grow till 190 gigaton in 2060, according to UNEP, or here are the data given on this slide of OECD. The prediction is almost the same there. That's, of course, an enormous challenge for delivering all these resources. On the other hand, we have to think whether we can cope with this challenge and whether we have all these materials and especially the metals, if we look at electronic devices, if we have these available. And I have to say that, we have to take care of how much we consume of these metals, since they are very valuable. And one aspect of the fact that they are so valuable is that the natural resource base for these metals degrades. And I mean with that the concentration of metals in the ores that we extract from the earth crust is degrading, is decreasing. If we look at this graph, it shows actually the concentration of copper in copper ores. 100 years ago, a typical ore had a content of 3% of copper. Today, it's much lower. It's a factor 10 lower, actually. So the ores that we extract today contain about 0.3%. So that's the first reason why metals are so valuable. A second reason is that many of these metals are actually byproducts of other metals, and we call them structurally scarce. So typically, one example is indium. We all use that. It's used for the screens in our smartphones, in our computers. And this indium actually is a byproduct of zinc extraction. And there is a factor of 3,000 difference in concentration. So if you want to, if the electronics industry needs more indium, that means that we should extract more zinc, but no zinc company will do that. Otherwise, the price of zinc would decrease too much on the market. So we call them structurally scarce. And the third reason why metals are so valuable is that these metals resources are concentrated in only a few parts of the world. And there is a concentration of ores, but there are also historical reasons for that. This graph illustrates this very well. There are some countries that have a quasi-monopoly on some of these materials, and then the trade of these metals is depending actually on only a few countries. So there are geopolitical issues related to that as well. On the other hand, the environment, we also have to consider that as a scarce resource. And the impact of extraction and production of materials on the environment is huge. The impact on climate change, that's the first bar you see, is more than 50%. So more than 50% of the greenhouse gas emissions can be related to the extraction and production of different types of materials. So that's a very important factor. And if we want to combat climate change, we also have to look at how we produce and how much we produce from materials and resources. There are other issues, of course. There is also particulate matter impacts that are related to metals and materials extraction, and biomass materials have a major impact on water stress and biodiversity loss, for example. If we focus a bit more on the smartphone, the first example that we took, we see that almost 80% of the greenhouse gas emissions of the lifetime of the smartphone can be related to the production of it. So the production phase is very important there. It's estimated that for one smartphone there is more or less 35 kilograms of CO2 equivalent emitted. In general, metals have a very large effect, a very large carbon footprint, and especially the metals that are precious and are needed for making electronics, such as tantalum, silver, gold, and so on. So the blue bars give the CO2 footprint per kilogram of these materials. And the red bar gives the footprint of recycling those materials. So you immediately see, we will come back to this afterwards, but you immediately see that recycling is very much beneficial for these materials in terms of CO2 footprint. And another issue is, so that's the impact per kilogram, but the other issue is that we need quite a lot of kilograms of materials to make our electronics. For example, computer on average contains 100 gram of copper, but for this 100 gram of copper, we need to mine to extract 40 kilogram of copper ore. So there is a loss along the value chain to make these computers. So the amount we need, you have to multiply this, of course, with the footprint per kilogram of these materials. Another issue, and it's a central topic in the MOOC as well, is the e-waste. What happens at the end of life of electronic equipment. And in general, there is in 2016 almost 45 million tons of e-waste generated, and a lot of them is contained in small equipment, in screens, in small IT, and so on. And issues with e-waste are just summarized here, but there is much more detail in the MOOC, of course. But the issues with e-waste relate to the complex waste streams and also the relative low volumes of e-waste. So to set up recycling, proper recycling schemes that are economic viable, that can be a challenge. On the other hand, there are also a lot of opportunities in there in this e-waste, or in managing this e-waste in a proper way, since the value of materials, actually the net value is more than 50 giga euro. And another issue is that there are a lot of toxic materials in this e-waste. So if it is not dealt with in a proper way, in a safe way, then it's a dangerous material, a dangerous stream. And so there is 2.2 million ton hazardous materials contained in this. Yeah, if everybody can mute his mic, then we don't have any echoes anymore. Yeah. Today, only 1/6 of these end-of-life devices are recycled efficiently. I will come to that afterwards, what that means. So that means that calls the raising attention for e-waste, the collection, recycling, amongst others, through extended producer responsibility schemes. And that e-waste will grow. In the future, we saw that the electronic devices that is growing, the materials consumption in general is growing, and also for e-waste that will grow as well. So estimations go to numbers of 120 million metric tons of e-waste produced per year by 2050. So that's something that we certainly should be aware of and should consider. So to summarize here the introduction, we have seen that there are issues with materials scarcity, metal scarcity. There is certainly an issue of impact of production and extraction of materials on the environment, on climate, and there is an issue of waste. But on the other hand, in contrast with that, we see that there is an increasing demand and growth of consumption due to increasing population and health, increasing wealth. It should be not health, excuse me for that. And so there is an increasing need of materials. And also the complexity of the devices we make is increasing. So as a final slide on this introduction, that means that these challenges actually means that the way we are producing and consuming today is not sustainable. So we do that in a very linear way. There is a high resource consumption that has effects on the availability of the materials, that has effect of the amounts of waste we are producing, and it has an effect on the environment. So we should go towards a more circular way of organizing the life of electronics and other products. We have to keep actually the materials that we once extracted, we have to keep them in the economy as long as possible and at a high quality of these materials. So that in consequence we consume less resources, that the impact on the climate is lower, and that we also avoid waste. This is a very simplified scheme of how it would look like. So at the end of the life of these products, we extract materials, we extract alloys, we extract also components, we recover them, and they stay in the economy. They are used for new products, for future products again and again. So these ideas are also contained within the Sustainable Development Goals. And if we talk about circular economy and recycling, it's mainly dealt with in SDG 12, more specifically in SDG 12.5, where it said that by 2030 we should substantially reduce waste generation through prevention, reduction, recycling, and reuse of materials. So I now come to the next question: what are then more sustainable options? And I will put a focus here on recycling, since that's the thing we would like to explain in more detail. So if we think about how we can implement this idea of a circular economy, what strategies do we have? Well, the most important thing there is that we should think of the type of functions that we want to deliver to the society. We set a bit aside the idea of making products. We want actually that people are able to communicate, and for this communication they need, for example, telephones, they need smartphones, and so on. So the function is central, not the products, how we can implement, how we can do this. For delivering that societal function, there will be emissions to greenhouse gas emissions, for example, related, and also there will also be resources related. So this societal function is delivered by products, of course. If we look at mobility as a societal function, we need cars, trains, planes, and so on. So if we want to be more efficient, we have to think of how can we reduce the number of products to deliver the same quality, the same amount of function. These products are made of materials. So also there are opportunities. We can think of how can we reduce the amount of materials we need per product. And finally, we also have we have to produce these materials out of resources, out of ores, or out of biomass, and there are emissions related to that. So we also can try to be more efficient in that way. So that this is a kind of Gaia equation that I like to use to introduce the strategies we can follow. So all these ratios, we can try to decrease them. For example, the number of products per function, we can decrease that by giving products a longer lifetime, by repairing them. We can also use them more intensively by sharing them, and so on. We can try to reduce the amount of materials we need for products by better design of products, by increasing the functionality of materials, but also by remanufacturing products. And finally, where we will go into more detail today, we can also try to reduce the emissions for the materials we need, or the resources we need for the materials in products. And a major strategy there is just at the right bottom. That's recycling and design for recycling. So yeah, the main strategies we have are reducing materials, improving materials, renewing materials. So let's have a closer look to one of these strategies. That's the recycling, and more specifically for e-waste. So if we look at the recycling schemes of e-waste, it's quite complex, since these products are also very complex, composed of a high number of different materials. So this recycling chain starts with the collection and the sorting of e-waste, then the dismantling of computers, dismantling of household equipment, and so on. And after this dismantling and the separation, we try to separate different material categories. These different material categories go to specific end processing. Metal steels are going to a steel recycling plant. The polymers and the plastic goes to plastic recycling. And also the printed circuit board go also to a specific integrated smelter recycling plant. So the recycling value chain is shown here as well. And typically we start with a very high number of users, of course, of these electronic equipment. The collection is done by 100,000 of different small companies. Dismantling, there are fewer companies. And if we focus on metal recycling, and more specifically for the recycling of printed circuit boards, for example, out of electronics, there actually are only a few companies in the world that are able to do that. Since it's very complex, I will not explain in detail, but that sketches a bit, the picture here sketches a bit the complexity of these flow sheets to extract the different metals out of these devices. And for example, a company such as Umicore, they are able to extract out of these printed circuit boards more than 17 different metals, going from gold to antimony, copper, and so on. So recycling activities today, and if we focus no further on these printed circuit boards, these recycling activities are very much focused on precious metal recoveries. And for other metals, critical metals such as rare earths, for example, there is actually little information available. Although there are some electronic components that contain quite some of these elements. For example, gallium is for 70% used, so 70% of the total production volume of gallium is used in electronics. So if we want to be circular in gallium, we certainly have to look how we could extract that better out of electronic devices. And there are also elements which are not well recycled at all, and that are mainly contained in electronics, such as beryllium, tantalum, rare earths. So these metals are found in all kind of devices, in capacitors. There is a large amount of tantalum used in capacitors. We don't recycle this at all at this moment. Also in the printed circuit boards, in the IC packages, mainly gold, chromium is there. There the recovery is quite well realized, and we have other devices containing rare earths, the hard disk drives, not that much use anymore in computers, but still in servers, and so on. So yeah, you will get the PDF. I will not go into details in these tables, but you will get a PDF of my presentation, so you can look into more detail there. Just one example, the rare earth elements are mainly contained, for example, in permanent magnets used in earphones, in mobile phones, also in the hard disk drives, but the amounts are quite low, and that's also one of the reasons that they are not well recycled. The amounts per devices are quite low, although there are new technologies under development, such as hydrogen decryptation, ion metallurgy, to recycle them. So recycling is important, as I said before, especially for saving resources, also for saving energy and the related carbon footprint. I put again on the right side the comparison between the CO2 footprint for gold, for example, for virgin gold versus recycled gold. So that's a very big difference. But on the other hand, we have to realize that also recycling needs some CO2 footprint at least. These are the red bars. We cannot escape from that completely. And it's not only about energy, we should also look at other environmental impacts, water use, and so on. I did a small calculation what the potential is overall of reducing CO2. On the left-hand side, you have the global use of materials in general, not only for electronics. On the right-hand side, the current CO2 footprint, and the blue part is the virgin materials. The orange part is the recycled materials. If we would be able to recycle 100%, we can obtain a reduction of 50% of CO2 emissions with the current technologies. And so I stress that there certainly will be innovations in recycling to improve or to decrease the energy intensity also of recycling. But today we could be able to reduce this footprint from 6.4 gigaton to 3.2 gigaton of CO2 emissions for these materials. That's a very crowded slide, but it says the same specifically for copper. If we would be able to extract all copper out of electronics and electric cables and so on, we also would be able to reduce by 50% the impact on greenhouse gas emissions. So I come to the last part. What are then the challenges? We have seen that there are a lot of opportunities, but there are also some challenges in recycling and I will show you 8 challenges. The first one is the complexity of electronic devices. If we again look at a smartphone, well, a smartphone is only a small device, but it contains almost 50 different chemical elements. All colored elements in this table of Mendeleev are used in this device. And the red colored ones are elements that are critical elements, which could suffer from a scarcity in supply. The blue ones are the ones that are the conflict materials as defined by the European Commission. These are the same as defined in the US, and the green ones are actually toxic elements. So we have to deal with this complexity when we recycle. A second challenge is that there are still a lot of inefficiencies in recycling, and especially in this automatic dismantling and separation. Since a lot of devices, such as computers, they are just shredded, they are just chopped into small pieces, and the pieces are separated physically into their major metal or polymer components. And that separation is not perfect at all. We did the tests, so we went to a recycler with 100 computers, old computers, and we measured on beforehand what materials these computers contained, and we followed these materials more or less towards the end processing. And what we saw is that the efficiency of recycling, so that's the number, the percentage of materials we can get out of this recycling scheme, pre-processing, dismantling, separation, pre-treatment, together with the final processing, is quite disappointing. So if you look at, for example, gold, silver, precious metals, so high value, yeah, the efficiency we obtained in a very high tech environment was for gold 77% and for silver, for example, less than 60%. Although in the end processing, if we deliver these printed circuit boards, for example, to a company such as Umicore, they are able to extract 98% out of it. So the loss of efficiency mainly is in this automated separation step, which is a challenge. A third challenge is, what do we want to optimize? The quality that we recycle or the quantity of the recycling? It's a very simplified example, but if we recycle the steel of a car body, most of it will not be recycled as steel for a car body, but as steel for construction applications. And that's due to the accumulation of contaminants in the steel, so that we only can use that for a bit lower quality. And the challenge is to guarantee the quality of the recycled material then. It's not a real problem there, since as long as the market for the steel, construction steels can absorb the recycled steel, there is not really a problem. But we have to be aware that there might be quality losses in recycling due to contamination. And one of the problems there is purely thermodynamics. I will not bother you too much with that, but if you recycle, for example, printed circuit boards in or other electronic materials in a copper converter, then some of these metals will end up in the copper melt, and then we can extract them afterwards, such as the gold, the platina, and so on. But other elements will end up in the slag phase, and then we can't recycle them anymore afterwards. So they are mainly lost at that moment. So that are the thermodynamic limits of metals recycling in pyrometallurgical recycling schemes. A fourth challenge is that we have to think whether it's better to extract the chemical elements separately, or if we can't recycle the alloy in which these elements elements form. To give an example, we did some projects on recycling the permanent magnets that are used for electrical motors and in e-mobility, for example. Most of them are made from neodymium boron iron alloys. We could try to extract, and we call that indirect recycling. We could try to extract the neodymium, the iron, and the boron separately, but that will cost a bit more energy than trying to recycle the alloy, so the material itself of these permanent magnets. So there might be more value in recycling alloys, but the challenge there is that the amounts will be smaller, so economies of scale can play a negative role there. A fifth challenge is that we always think, well, engineers, I'm also an engineer, we think of better recycling as better technologies, but there are other aspects related to that. For example, we really need better designs of these devices so that recycling is already anticipated in the way that these products are made. We have to design better collection schemes via, for example, extended responsibility. And we also need to know better what materials are contained in products and when they are coming to the recycling market. So these are aspects of recycling that are less related to technological aspects. The sixth challenge is that all incentives and legislation that I know are weight-based, and so it's stated to recycle that percentage of the weight of materials. But that does not say anything about the value of these materials. So small amounts of materials, such as the metals into electronics, can have a very high value. So the value share for gold, for example, is in a mobile phone is 70%. So yeah, and the weight share is very small there. A seventh challenge is typically for the challenge for the industry. That's about the volatility of prices of materials. So if the prices are just jumping, then it's very difficult for the recycling sector to have a stable business model. So so the governmental agencies should be aware of that and should be think of possible schemes to alleviate this volatility of the prices. And the last thing is actually coming back to the strategies for circular economy I've shown you. Is recycling always the best option? Yeah, in these graphs gives actually the CO2 we can save by implementing different strategies. And we see that actually the reuse of components, yield loss reduction, scrap diversion, yeah, we have still margin to grow there, but the major effect for steel and for aluminum recycling, at least, is in life extension of those products, is in more intense use. So for me, recycling, we have still to grow a lot in efficiency, in safety of managing the end of life of these devices, but we should not forget that other strategies are important as well, and very much important if we want to go to a circular economy and to a low carbon economy. So to conclude my webinar, yeah, I've seen that resource scarcity and environmental impact urges us to find new ways of managing materials at the production phase, but certainly as well at the end of life phase of products. That we find yeah, a lot of opportunities in sustainable recycling, but we should also be aware of the challenges, and I hope that I gave today a nuanced view on that to you. And yeah, these solutions have to be accompanied by better monitoring of these waste streams, better knowledge of material flows and impacts, also of consumer behavior. I didn't discuss that, of economic incentives, also changing legal frameworks, social aspects as well. I couldn't discuss all of these things today, but of course they have to be considered as well. And we need a lot of experiments to further grow in this waste management. And finally, don't forget that the resources of tomorrow actually are not only found in mines, but they are everywhere around you. And sustainable materials management certainly opens a lot of innovation opportunities, such that material resources that were considered as infinite and free to use, that they will not become a problem in the future because of scarcity, but that sustainable recycling can deliver these resources for future applications. So I thank you, and I hope that, yeah, here are my coordinates, and I hope that I still can answer some of the questions. Thank you.
Thanks to you, Karel, for this very interesting presentation, and my apologies for starting late and the issues I had on my side on my sound. We do have some. Can you please mute your microphones, all of you, for the time being? Thank you. So we are now going to open the questions and answers session, and if you wish to take the floor, please do not open your mic straight away. Just click on the raise hand icon, which is at the right of your name. Once you have been given the floor, please unselect the hand, and by clicking on it again, When given the floor, remember to unmute your mic and then to mute it back after you exchange. In case you have any problems using your mic and wish to ask any questions related to the presentation, you can send me a chat message to BRS Convention Secretariat in the top-down box of the recipients of the chat box. The presentation, as I sent you a message before, will be available for download shortly, and will also be sent in a follow-up email to this session. A recording of the presentation would be posted on our website on Monday after the second session of this webinar. So you're most welcome now to bring any comments or pose any questions you have on Karel's presentation. So to do so, please click on the raise hand icon or send a chat message. Thank you very much. I see that Alexandra Ribeiro has asked for the floor. Please unmute your mic.
No, thank you. It was, I don't know. It was, I just want to thank it. It was a very, very interesting webinar, but I don't have any questions for right now. Thank you.
Thank you very much. I see some comments coming in the chat from Rafael saying very interesting presentation. Thank you very much. And Victor Melas is asking, do you know of a low cost or low investment technology to recover precious metals? Second questions would be, what would be the fee for the MOOC? Karel, please go ahead.
Yeah, the fee for the MOOC, that's up to you, Dan. That I don't know whether you can comment on that.
Then I'll let you answer for the on the questions on low investment technology to recover precious metals.
Okay, yeah, it's correct, and I understand with this question that you refer to the pyrometallurgy technology that exists today, which is very expensive. And as I showed in the webinar, there are only a few companies in the world. You need a large scale for that, and that's indeed a very expensive investment. But there are actually also research projects and innovations that are looking whether there cannot be hydrometallurgy used for recovering precious metals out of electronics, even with leaching, for example. If that could not be used, that will be probably less efficient and have a will last longer to recover the metals, but that might be much more or much lower in investments indeed. But I'm not aware of commercial applications at this moment, unless somebody else knows that.
So thank you, Karel. I'll answer to the second question earlier on the fees. The fee for the MOOC is there's no fee for the MOOC. It's a free course, so everybody is most welcome to join, and at no financial expense on registering. I'm just looking if we can. If you do have, I see a lot of comments coming in through the chat. If you can intervene with the raise hand, it would be nice. So thank you. I can see Vikas Shetty. Please open your mic.
Hello.
Yes, please go ahead.
Karel, it was indeed a very nice presentation.
Thank you.
I am from India, so I wanted to know. I mean, most in Indian context, 95% of the e-waste recyclers, they are from the informal sector, and in these people who are involved in recycling the products, they burn the plastic to extract the metals. So I mean, I didn't. If you could highlight how, in a way, we could, resolve the issue of burning of e-waste, as well as because it leads to release of lot of other toxic chemicals, so which is harmful for them, and I mean primarily BFRs. So could you please suggest something on that, or what's your view on that?
Yeah, thank you for your question. Indeed, I didn't cover these issues, but this is a major problem. Indeed, burning that in open air, especially when there is, for example, PVC involved in the insulation, that causes dioxins and things like that. So it really is a problem. But on the other hand, we have seen that the efficiency in the informal recycling sector, such as in India, is much more efficient in collection and in separation of materials. And what I would suggest is definitely to make use of that efficiency. If that could be combined with some more company-based, more professional end processing of these materials, that would be a very good combination. But then, of course, these people have to be given a fair price for collecting, for separating these materials. And I know some initiatives, such as in Ethiopia, for example, and Kenya, that are initiated together with companies in Belgium, where computers are disassembled and the steel and the aluminium and the plastics are recycled in plants in Ethiopia, and then the printed circuit boards are sold and sent back to companies such as Umicore we have here in Belgium for the end processing. So the combination actually of this informal sector for the collection, for the separation, also for the recycling of the pure steel, aluminium, also copper, if that can be separated in a proper way, with the more formal treatment or economy for the end processing. That is actually a combination that we should strive at, to my opinion.
Oh, thank you.
Thank you very much, Karel. Thank you for the question also. Karel, I've sent you quite a series of questions which have come through the chat box. Can you please have a look and answer the ones which seem most relevant to you? I'm sorry, I wasn't able to make a selection in them.
So in the chat box itself?
Yeah, I've addressed them to you in the chat box.
Yeah. I see the question about the ways for assuring or incentivizing at the collection level e-waste managers. That's a very good question. Also here, or even more in industrialized countries, we see that people are not keen on just sending back their mobile phone or their computer. So I think with a scheme of tax and repay funds, for example, on these products that should work better. We have a lot of experience here with extended producers' responsibility. It worked very well when it was installed. We have seen an increase in efficiency of collection and recycling very much in the first years, but then it stagnated a bit. So again, new incentives have to be, or the incentives have to be refined then to even collect better. So, but there are different schemes such as extended producer responsibility, tax and repay, of products, that really helps. Yeah, there is also a question about using recycled materials and what can be done to make them working as good as virgin materials. Well, for the metals I discussed, indeed for the steel and aluminium and so on, there is some contamination, but they are not very structural in these electronic devices. So there, it should not really be a problem to use recycled. It is a problem when it's really the mechanical properties, for example, are extremely important, or electronic properties are extremely important. So if it is just for a casing of a product, that should not be a problem.
Last one is anything that comes under this. Sorry.
Okay. Yeah, there is so much text in these questions. I'm sorry.
There's a lot, yes, there's a lot coming in there. So I'm checking if I can see other persons raising their hands. I see that Yangar M has asked for the floor. Can you please open your mic? Please go ahead.
Thank you. Actually, thank you for an interesting presentation. My question is, given the fact that bulk of the e-waste is plastic, are there any technically and financially feasible option for plastic recycling from e-waste?
Yeah, for the plastic recycling you are asking for, eh?
Yeah, actually, plastic mean you know that plastic from e-waste is not normal e-waste, normal plastic.
Yeah,
I
know.
It will be treated separately. So.
Yeah, I know. That's a problem. I have to be honest with that. That's really a problem, since a lot of these plastic casings, for example, of e-waste contain flame retardants, with bromine in it, for example, and yeah, that's not in recycling not very well. It is not very. It has an impact on health. There are several health issues related to that. So the problem is also if we recycle a lot of these plastics, then we dilute actually these flame retardants in these plastics, and yeah, there is some proliferation of these toxic products that should be avoided. I don't have a solution for that, except of recuperating then the energy in incinerating these plastics, or the only solution is if you are able to set up a closed loop recycling, so that you really contain that type of plastic within a certain product category. But that's quite tricky and quite challenging to do. So to stay at the safe side, I really think, and to make these closed and open loops of materials, to make them clean and safe, I think this type of plastics containing flame retardants with bromines, for example, I think that these ones have to be incinerated at last.
And I noticed that Gerardo has asked for the floor. Gerardo, do you want to take the floor? We might take this question and then evaluate if we continue. And in the meantime, I'm going to make Kaja's presentation available for download on screen. Gerardo, please go ahead.
Can you hear me?
Yes, we can. Please go ahead.
Okay. Hello, good afternoon, Carol. Was a nice presentation. Well,
Thank you.
the last comment about the plastics. I'm expert in e-waste technologies. We are manufacturer for specific recycling plants for e-waste, and we also do plastic recycling. This is possible. We can separate the flame retardants and all the hazardous plastics.
Okay, good.
From the rest, and we can separate also all the other plastics, PP, PS, PE, etc., etc. So finally, we will have really good plastic recovered. But the problem, I think the general problem of recycling is that this costs money. That is the most the biggest problem when we look worldwide. So only in Europe we have the PRO system, the extended producer responsibility organization is working properly. That means the producer pays, okay, and this fee is used to pay recycling. But when we look worldwide, I'm a lot of time in Africa, US, Asia. So when we would do the same effort in the rest of the world, like in Europe, so your numbers will completely change, you know. And technically, it's a lot of things are possible. My example for the plastic, but this is very expensive, and everybody or the recyclers are looking for the benefit, you know. And this is I think this is a big problem. The finance of recycling, and the invest and all that things.
Thank you for your comments. You are completely right. There is a lot of, or there are a lot of possibilities at the technology side, but of course, the more complex it becomes, the more expensive it also will be in economic terms. But also, we have to also look whether all recycling schemes are then still environmentally beneficial in terms of energy consumption and things like that. Since I know, I don't know your processes, of course, but I know that some types of chemical recycling of plastics, for example, are very interesting to deliver a high quality, to recycle everything. But if you look at the energy consumption, then it's more than using virgin plastic. So then you don't do that anymore only for recovering materials, but then you also have to do that to, let's say, clean up the waste, and that's indeed expensive. And then as society, we have to decide whether we want to invest in that or not.
Thank you very much, Gerardo and Karel. Gerardo, a participant has asked you to share your company contacts. So please have a look at your chat box, and you can maybe answer the person who's interested in plastic recycling as well. A person has been
yes, of course, no problem.
Thank you. Shelly Mitchell has been trying to raise her hand but couldn't manage. Karel, she wanted to clarify if she had heard correctly that 50% of greenhouse gases is caused by extraction and production of e-waste.
No, not of e-waste. The 50% of the global greenhouse gas emissions. So all emissions of CO2, methane, and so on together, that causes climate change. 50% of that is related to extraction of materials in general as well, not only electronics. So it's not related to the problem of e-waste only.
Thank you for the precision. A question from Hobby Rakotondranali reads, thank you for the insightful presentation. The fact that we only have few companies in the world able to extract metals from printed circuit boards, does it mean that developing countries have no alternative apart from exporting fractions abroad? Would it be interesting to partner with developed countries in recycling technologies transfer? Thank you.
Yeah, that's a good and a difficult question. Yeah, so that depends a bit on the volumes of printed circuit board wastes, so to say. The investments for new facilities are very big, and you should consider that as or that should become, I think, in the future, a more joint efforts also between countries. I don't know whether it's not worthwhile to do that right now in developing countries, and that's really market depending. But personally, I think there are a lot of opportunities already in other types of recycling, in this dismantling, in better collection schemes, that it might be more efficient from an economic point of view to first invest in those things before looking at this end processing.
Karel?
Yeah.
I think we are getting to the end of the time allocated for this session. I would suggest that we are on our side going to compile all the questions that have been posed and the answers we received, and see if we can forward your questions to the presenter and maybe get some responses, which we can then publish on the dedicated webpage of this webinar. Would that be agreeable to you, Karel?
Yeah, that's fine with me. Yeah.
Okay. So then, kindly note that I've had some messages from some of you saying that they cannot download the presentation, which is on their screen. I am going to send it in a follow-up email after the session, so don't worry. You will receive a copy of Mr. Van Akker's presentation. I thank you very much for your participation and interest in this session. I would also remind you that an additional session for this presentation is scheduled next Monday, 24 February at 10 in the morning, which is GMT +1. And further to this, the next webinar of the series on the e-waste MOOC will address e-waste and children's health and is scheduled for the second week of March. The specific dates are still to be decided, so once there are invitations to register will be sent shortly after. I will now close the meeting. I'd like to thank Karel once again. Thank you very much, Karel, for your time, and
thank you all for attending.
And thank you for the very the big amount of questions which have come, and I apologize we couldn't take them on all in this short time we had. So thank you again, and maybe see you Monday, and we look forward to seeing you in the future webinars on the MOOC. Bye-bye.
Bye.
Thank you. Bye-bye.
Bye-bye.
Right.